Hello everybody, this is just kind of a follow-up video real quick to go over again how we would solve polynomial inequalities. So inequalities that are not just linear but like really higher order polynomials, higher degree. So we had a kind of like a three-step process that goes with this. And step one would be this. You see that we have our polynomial inequality here, 2x cubed minus 3x squared minus 32x is greater than negative 48. But the first thing we need to do is this. We would like to find the zeros of this polynomial. So now I know it's probably tossing some people out the fact that we don't have an equal sign here, but I do want you to consider that if this were an equal sign, I said, yo, go solve this. The first thing we'd want to do is probably set it equal to 0 and try to factor it. And if we can't factor it, of course, we'd use synthetic division possibly. But the bottom line is this. It is not equal to 0. That is, I say that very, very loosely here because it's not equals in the first place. It's greater than. But what we do need to do is we need to get this expression on the left right here. We need to get this such that it has a 0 on the right. We want this to be 0. So the first thing we're going to do is we're going to add 48 to both sides. That's just, I point this out because, people are probably pretty good at these. I show them how to do it. And they do okay. But once I start throwing non-zero expressions on the right, they're like, whoa, what do I do? So minus 32x, we'll say plus 48. We still have a greater than, is greater than 0. Okay, so here's the deal. When solving polynomial inequalities, the first thing we want to do is find our critical values. That way we can set up our, what we call test intervals. Okay, so first things first. Before we find the zeros of this, the awesome thing is, if you have a graphing calculator, let's face it, you should probably graph this expression first. So we say, what we're really after here, and keep in mind that our original expression, this thing right here, let me go back to that like fuchsia color or whatever. This expression right here is kind of like our f of x. And what we're really saying is I want to know, well, hey, what are all the x values that would cause my function to have positive y values to be greater than 0, right? So when we come over here and we go to our graphing utility, I say, all right, well, you can kind of see up here, I've got the inequality and I've got just the function itself, but this function right here, I'm going to graph it. I say, boom, okay, well, now I'm really zoomed out, everybody, but I do want you to see this. You can clearly see that, and I'll zoom in here, but you say our function starts down here. Its end behavior is starting way down at negative infinity, but it's going from negative y values to positive y values. It goes up and up and up and up, and then it starts to creep back down again, and then it falls back down to negative y values again, and negative, 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 and it pops up to positive y values. But of course, recall that we are concerned with what are the places on my x-axis that when I plug in those x values, I get positive y values. So that zoom in thing I said I would do, well, here we go. Essentially, I would like to know, okay, so again, let me get a clearer picture of the x-axis here. What were all of the x intervals, okay, intervals, entire intervals for x, for which my function has positive y values? That is, what are the x values that when I plug them in, I get, y values that are above the x-axis. So you can see here that when we do this, we're going to find some critical values, which involves, finding the zeros of this function. But first of all, you see our critical values must be negative 4. Looks like 1.5, or you're going to find it's 3 halves. When we say positive 4, the bottom line is this. It's just the case that this function, we say if negative 4 is a critical value, then one of our intervals on our x-axis is from negative infinity up to negative 4. But you'll notice this, all of the y values from negative infinity up to negative 4 on our x-axis, all of them are negative. And it's not that, it would never be the case that you would choose some x values on that interval and plug them in and you'd have your graph above the x-axis, and then some of them would be below the x-axis, because if that were the case, if it was going from above to below or below to above, you would have crossed the x-axis in the first place and we would have had a critical value. So it seems to me, just looking at this right now, from negative 4 up to 1, our graph was above the x-axis there, and then from 4 on out to infinity. But of course, we're supposed to be doing some really good algebra here. So let's go ahead and do our process algebraically, and then we'll go back and look at the picture. Okay, so the first thing we need are our critical values, which means we're going to need to find the zeros of this polynomial function. So it being a four-nomial with third degree, it lends itself very well to what some people call the chunking method, and this looks like multiplication right now. I'm going to squeeze a plus in here, but this negative just has to go with our 32. So we say, all right, well, what common factor do our first two terms have? And they have a common factor of 2x squared. So factoring that out, we say, well, x squared, and that leaves behind 2x minus 3. So we have x squared times 2x minus 3 plus, this is that plus sign right there, plus, now we can factor out a looks like a negative what, 8? Negative 8? No, negative 16. That works better. Sorry. Negative 16, and then we say that would leave behind also 2x minus 3, and this is still greater than 0. So now, noticing that these two terms, what they have in common is this 2x minus 3 quantity. We will factor that out front, right out there. We say, okay, so what's left is this, 2x minus 3, and that's times x squared minus 16, and this, of course, is greater than 0. And you might notice that this is a difference of 2 squares. So again, we'll just proceed. Again, we say 2x minus 3, x plus 4, x minus 4. So now this is completely factored, and we could say, well, if this was equal to 0, then our zeros would be positive 4, negative 4, and then, you know, of course, if we set this factor equal to 0, we'd add 3 divided by 2, but we get our critical values. So let's write this down. I say critical x values, critical vowels. We say our x equals, and we want this in usually increasing order, so we say negative 4, we have 3 halves was another value, and we say 4. And we put this in increasing order because what we're going to do is we're going to set up our x-axis over here and set up our test intervals. Okay, so we say if this is 0, we say 1, 2, 3, 4, 5. We'll go 5 in the other direction. I'm going to compact those a little bit. 3, 4, 5, negative 5. Okay, so we say our critical values happen to be negative 4. We had a critical value. We had a critical value at positive 3 halves. Okay, so 3 halves. And you might see how this, of course, relates to the graph that we had drawn on the other page there. But we say these were the intervals for which our function, I mean, if you're looking at the picture, goes from being negative values to positive values or positive values to negative values. So we just want to know, so what intervals of x, for what intervals of x here would we have this thing on the left greater than 0? So again, looking at the picture, we say, well, we had positive y values between negative 4 and 3 halves, and also from 4 out to infinity, but the bottom line is this. We say we have some intervals here, and our intervals are from negative infinity up to negative 4. That's one interval. From negative 4 up to positive 3 halves. We say from 3 halves up to positive 4, and then from 4 on out to infinity. These are the 4 intervals for which we're going to test some x values. I want to know which ones would cause us to have positive y's. So if we were to choose, say, representative x values, I like to plug in easy things first. But let's just say we plug in 0. It's clearly between negative 4 and 3 halves. I know I'm skipping around, but if I plugged in 0, so now going back down to our factor, this is the factored expression I want to work with. You'll notice if I plugged in 0, I would get here negative 3, okay, times 0 plus 4 is 4, times 0 minus 4 is negative 4. We're saying greater than 0. Now, it is not actually the number that I'm concerned with here, it's just the sign. And I notice I'm taking a negative times a positive times a negative. In other words, like a negative times a negative is positive. We get a positive number is greater than 0, which is certainly a true statement. So of course, if 0 is true, we'd shade it in, but you know, our knowledge of inequalities, we say, well, then anything in this interval from negative 4 up to 3 halves would certainly make this true. Okay, so I hate to take those things out of there, but I just wanted to get that out of the way here. And we did test 0, and it still makes it true, but we'd say, okay, so from there to there, we have values that would cause our y values to be positive. Let's say we choose 2. Now we're going to choose 2. And we know by looking at the graph, at x equals 2, we have negative y values, so those would not satisfy the inequality that these things come out to be greater than 0. But what if we did choose negative 2, or pardon me, 2? So we'd have 2 times 2 minus 3, that's 4 minus 3 is 1. And then we'd have 2 plus 4 is, that's 6. And then here we'd have 2 minus 4, that's negative 2. So in other words, we have a positive times a negative, which is negative. And so this statement would read, a negative number is greater than 0, which is certainly not true. So basically what we're saying is, well, we chose 2. 2 didn't work. So anything on this interval from 3 halves to 4 is also not going to work. And so now, for the sake of time, I do want to say, well, we would choose 5, say next would be the next one I would choose and test it. And we know by looking at the graph that 5 works. You know, everything from 4 on out. And I'm going to put open parentheses here. The reason why is because if you were to say plug in the critical values themselves, well, we know that makes it equal to 0, and that's not the same thing as greater than. That would, you know, if this was greater than or equal to, we'd put closed brackets there. Those would work. But essentially, here's what I'd like to do. Now, if we go back over to the picture, and I realize that, hey, your graphing calculator, man, it doesn't do this for you, and I'm really sorry. But just to give you an idea, if I were to now highlight this, what this is doing is it's highlighting all of the x values that when I plug them in, our function had positive y values. And if I were to zoom out, you would see that this is necessarily the case. But zooming out, it's kind of hard to see. But anything that's not shaded in right now, those are all x values that when you plug them in, you'll notice that our graph was, like, say, below the x-axis or had negative values. And in this case, we wanted all the x values that when you plug them in caused it to be above the x-axis or greater than 0. So yeah, that's what we're after. What are the x values that cause my function to be greater than 0 or above the x-axis? So I bring up the graph thing because it's really good to get the concept of being able to look at the graph and being able to tell where your function is either positive or negative.